Welcome back. Today we are going to be working on question 6 of the winter 2022 midterm. Um, this question is a multi-cycle data path design question. And so we're going to be asked to slightly modify the LC2K multi-cycle data path to have a couple of new instructions. So let's take a look. Yeah. So this question asks us to add the following instructions. Set stack pointer, push, and pop. And so they say we've added a new register called stack pointer. And so I'm seeing that. What color am I using? We see that up here. And then we need to support all of these operations. And then part A says we need to complete the design by drawing connections. Your design should enable the least number of cycles. Note that we can extend any of the muxes, but we can only add one new mux, and only one of the muxes can have more than 4 inputs. New constants can also be added to the muxes. Awesome. So let's think about what this stack pointer register is, because I think it's useful sometimes to just have a little bit of context. So back in 2C, you all should have become a little bit maybe familiar with the idea of having a stack pointer, which is just a location. It's essentially just a pointer to a location in memory. And when we want to add something to the stack, we call it pushing it to the stack, where we'll set the value at the stack pointer to a desired value, and then we will increment the stack pointer. So it points at another location, and that way you can like grow the stack, but eventually you might want to recover values from the stack. And the way you do that is you pop, which means you're going to decrement your stack pointer, and then you're going to grab whatever value is located at that spot in memory. What we didn't really see was in project 2C was this idea of set stack pointer. But it is something essentially stack pointer set stack pointer just kind of relocates the stack pointer. So we have essentially stack pointer is just another register. So it's probably going to hold one word, which is allows us to address the memory location. So the way I like to do these questions is kind of just work through or work straight down through our instructions and modify what's needed to support each pseudo. Like we usually give you like some sort of pseudo instruction here, and we can if just by following that pseudo instruction, we can kind of figure out what modifications need to be made. So first thing I'm looking at is that set stack pointer. So in a set stack pointer instruction, we are going to override the value that's in stack pointer with the value of register A. So the way I can write to something is probably this input wire, and the way I can like read the stack pointer is probably this output wire. So if I wanted to read the value of register A and insert it into the stack pointer, well, the location of the value of register A is this O1 right here, right? So register A was specified as R1, and so that gets translated into output 1 of the register file, which is a value of register A. So if I wanted to override the stack pointer with that, I would probably want some sort of wire coming out of my register file and entering my stack pointer. So that's a little bit offset, and I'll explain in a second just why. So that's one place that we're writing to the stack pointer. I'm looking at the rest of my instructions, and I see that there's 2 other places where we write to our stack pointer, right? We're assigning the value. And in both of these locations, it's going to be either stack pointer +1 or stack pointer -1. Well, we only have one place in our architecture which is going to be able to perform the computation of addition or subtraction, right? And that's the ALU. So essentially, stack pointer minus 1 and stack pointer plus 1 are going to be coming out in ALU result, right? So essentially, I can modify my architecture so that ALU result is the other potential input to the stack point. And so because these are going to be executing dependent on instruction, I'm going to have a mux here that allows me to choose whether I want to write reg A or reg A or the ALU result to our stack point. So that covers writing to the stack point. So let's move on to the next instruction. Now that we've kind of finished thinking about that. Excuse me. Oh, shoot, I just disconnected that. This wire is very loose, so it disconnects sometimes. Please. Oh, nice. Okay. So now in push register B, we are performing a memory access at the stack pointer, and then we're writing that back to register B. So essentially, how do I access a stack pointer? Because I'm going to be reading stack pointer, right? So it's going to be something connected to this output here, right? So how do I modify my architecture such that I can perform memory access with, I guess, address, right, being stack pointer? Well, one option that comes to mind is because my my bottom mux, my mux ALU2, that's this mux right here, has a 0. I could use stack pointer as an input to it, right? And then I could just add 0. And that would give me my ALU result of stack pointer, right? Because stack pointer plus 0 would be stack pointer. And then I could, because this ALU result extends or is connected to my mux address right here, I could use that. The reason that might not be the best solution is because we're not trying to minimize the number of changes that we make to the architecture. What we're trying to minimize is the number of cycles. And so if we don't have to perform an ALU computation for at that stage, let's not, right? So let's instead connect the wire for the value of stack pointer straight. Sorry, I can't draw straight lines. Straight to the mux that chooses the address, right? So it's another option for that mux. And so what that allows us to do is it allows us to access mem at stack pointer, right? And then we don't have to, essentially we need to double check that we can assign that to reg B. So that value would come out of the data register right here. And it looks like, because we have this wire, it has a way of making it to data in. And so that's the only modification we need to make there. So then we can look at this instruction right here, our pseudo instruction, which says stack pointer is equal to stack pointer plus 1, right? So essentially, we have to do a couple things here. So first thing we have to do is we have to be able to read stack pointer, right? And then I need to be able to add 1 to them. So essentially, if I think about it, like the only thing I have on my architecture that can form addition is the ALU. And so on the 2 inputs, the ALU must be stack pointer and the value 1, right? Well, I already have the value 1 available to me through that bottom mux, right? In mux ALU2. And so if I read, I'm going to change colors here really quickly so you guys can still see. Oh, wait, that will not turn out how I want it to do. Okay. Since I still want to be, I want to read that 1, right? So I'll get the 1 there. essentially I need the stack pointer to be here. And so essentially I provide a wire between my stack pointer out and that top mux such that I can get my stack pointer in the top there. So that allows me to read stack pointer, right? And then we made this modification earlier, this one right here, which allows me to take the result of that, which would be stack pointer plus 1, and write that back to the stack pointer. So now we're successfully, with these current modifications, we're able to do, oh my God, that was the worst check mark ever. We're successfully able to do a set stack pointer. We're successfully able to push to register B. And so now let's look at pop register B, right? So pop register B says, first, I need to be able to calculate stack pointer is equal to stack pointer minus 1. So this is going to be really similar to the plus 1, except instead of adding 1, I have to subtract 1. Or if I think of it, because my ALU can only perform additions and NORs, I could think of it as adding negative 1, right? So I already have the ALU, the stack pointer available in the top mux. And so if I wanted to make the stack pointer available, so essentially the negative 1 has to come from the bottom. However, currently I have no way of really subtracting 1, right? Accessing an immediate negative 1. And so we're going to extend this bottom negative, we're going to extend this bottom ALU2 mux such that it has negative 1 as a potential input, right? So for my iPad, reconnects, pretty please. Please. Oh, it popped up for a second, I believe. Come on. Oh, there it goes. Okay, so if we extend the bottom mux, so it has a negative 1 immediate value, right? Then I can, the bottom ALU input will become negative 1, and the top ALU input will be the stack pointer. And so as a result, we can calculate stack pointer minus 1, and then again, we'd write back through that ALU result top wire. Okay, the last thing that we need to check is if we're able to do the reg B is equal to mem at stack pointer. So let's think about what it would take to do that. Essentially, I need to be able to, I'm going to go ahead and apologize. Earlier on, when I drew this wire all the way up here, right, that allowed me to read the stack pointer and access the location in memory. But when I talked about writing back here, this was allowing me to write register B, right? So we're able to do this by extending that top wire because we can take the output of mem, right? And if it's in read mode, then I can write to register B with mem at stack pointer, right? However, back in that push instruction, if I wanted to do mem at stack pointer is equal to register B, right? So this top wire still applies because that gives us mem at stack pointer. But if I would instead put this into like write mode, if for a push instruction, and the value that I would assign would be so register B's value. This is reg B's value. It is propagated through this wire, and it comes in through here. And so we can assign reg B already. So these are all the modifications that we need to do. To recap, we added this mux here. We added the 2 wires that come into it, one coming from register A's value and one coming from the ALU result. We also had the stack pointer output going into the mux address, because I need for both the push instruction and the pop instruction, I need to be able to access the stack pointer as the address for memory. And then I also had it as an input to the ALU, so that for the same instructions, I need to be able to read that as an input into the ALU. And yeah, that's all the modifications that we made. Awesome. So now that we've done part A, part B asks us to specify the operations for the remaining cycles of the pop instruction. So data reg stores the value read from memory, and stack pointer stores the stores the value of the stack pointer register. You do not need to fill in all the blanks. Okay, so let's take a look at our instructions. So that. Wait a minute. Okay, so if I was doing a pop instruction, right, there's two pseudo things that I need to do. I need to calculate the new stack pointer, right? And so if I were to like decompose, I'll do this in black, right? So if I were to decompose this instruction, right? If I were to decompose this instruction, I would initially want to calculate stack pointer -1, right? And I would like save that to probably the ALU result. and then I would store the stack pointer in the ALU result, or sorry, I'd assign it the stack pointer to the ALU result. And then in the second instruction, second sub instruction, we need to access, we need to set reg B to the memory address, right? So first I need to, I need to load, I have to do the mem access. And then once I've done the mem access, then I have that variable, like that'll be stored in the data register. And then I can say reg B is equal to the data reg. Awesome. So one thing to consider though is like the ordering of these pseudo instructions. The stack pointer that we are using right here needs to be the stack pointer that is signed here. So essentially, it needs to be stack pointer -1. And so that's an important consideration to make as we go ahead and do part B. So I mentioned this earlier, but the first thing that we need to do is we need to calculate the new ALU result, right? We want to calculate stack pointer -1. So to do that, I'm gonna use a color other than white. We can do ALU result is going to be equal to the value of the stack pointer -1, right? Is there now we look back and we think about, is there anything we can do else we can do at this point? Well, we can't execute stack pointer is equal to ALU result, right? Because that needs to happen after we calculate the ALU result. So can we perform the mem access, right? Can we perform mem at stack pointer? Well, the answer is no, because we need to wait for our new stack pointer to be calculated, right? So we can't do anything at this point. That's all we're going to have for cycle 3. So then for cycle 4, what's the next thing we can perform? Well, one thing we can do is we can do stack pointer is equal to ALU result now, right? So this is the update part of the instruction. And so the stack pointer is now going to be assigned to the ALU result, which remember is the stack pointer -1. Well, can we now perform the memory access, right? Can we now perform mem at stack pointer? While it's true that our stack pointer is not going to be updated yet, we know that the value that will be in the stack pointer is still in the ALU result. So we can totally use that ALU result value to perform the access, right? So I could say my data reg, right? Because that's the output of memory. My data register is going to be assigned to the mem access of my ALU result. So lastly, so essentially we've performed the first pseudo instruction. And if we're looking at the second pseudo instruction, the last thing we need to do is assign reg B to that data register. So we can go ahead and do that. And we are done. Awesome. That's all I have for this question. Hopefully you found that helpful. I'll pick up on number 7 next.